Hello to everyone. Well, we are solving today this exercise, the E91 of metric geometry, the part 1. But we are going to solve E91 and E92 because they share the same statement, although they ask for different things. So the statement is as follows. So we have given the planes ABC and ABD. We need to define a line R that start in point D and form an angle of 50 degrees with ABC, with plane ABC, and an angle of 30 degrees with ABD. Yeah, and yeah, it is coincident at one point with the point D. Then, taking into account the possible solution of R, we have to calculate the minimum distance between R and C, which is this point. That's in E91, and in E92 is essentially the same angles. But then once that we find the solution for R, we need to compute the minimum angle between R and AC, which is this segment. So we can do both at the same time. Okay, so this is a typical problem of an angle between one line and two planes. And yeah, we have here in theory, if you have read this and make watch the videos, you can have here angle between a line and two planes, and there are many different ways to solve it. Yes, and yeah, I will solve it in a few different ways. So let's see. So you have different methods to compute it. Yes. So as usual, this is the statement that I downloaded from here. Clicking here. So yeah, as usual, we go to a 3D sketch where we will find the solution. And we will find the first solution, which is what we are going to do is, as usual, we will go to do the angle between a line and a plane. Okay, so then you need to take into account to get the points, and yeah, so for example, yeah, this ADB, which should be ADB. If you want, sometimes you can, in exam or anything, you can write a notation here, insert. Let me go down, annotations. So if you want, you can find a note here. For example, this is going to be D. And this is C if you want to. And this, yeah, this I think is A, but anyway. Okay, so the first solution is, like we can draw a line between point D and yeah, we can model the line, yes, we want to. And then we said that this line have an angle with ABD, and we draw, we measure the angle between this line and the projection. So this is in plane ABD, we can already find the parallel to the plane and the perpendicular. Yeah, so we can say that this is parallel, but it will be on plane because this point is on plane. And you see that we can move it. So we made this perpendicular to the plane. Yeah, and we measure the angle with the parallel. But I forgot the angle ABD is 30 with ABD. Yes, so it's going to be 30 degrees. Yeah, however, we also know that we will have another solution for this particular angle that will be something like this. Yeah, maybe we can use the same point here. We make it again perpendicular, but it's the same to say that it's collinear, and we measure the angle. Yeah. So these two lines, they form an angle of 30 degrees with ABD. And indeed they are blue because we can move them as we want to, but we need now to find ones at least 50 degrees with ABC. Okay, this might be maybe something like this, and then we do the same with this plane ABC, and the angle this was, I think, was 50. Yes, so again we make the perpendicular and the parallel. Yes, so this one is going to be parallel to ABC, and this one will be perpendicular. Yes, and the angle is between my line R and the parallel. So this is 50 degrees. And then this one I think is 50 again because they share the same point. Yeah, so we found two solutions. Yes, but we have more solutions. Indeed we have four. Like we have two solutions for 30, and we will have two solutions also for 50, and they can be like here and there or here and there because they are collinear, so it's only for four solutions. So then I can do exactly the same. Yeah, and then I can do from here to there, this one and this one perpendicular. I put this angle, so this is the parallel, so this angle is 50. And I will need to check if this is 30. I don't know why I cannot move it, but it's probably because I need to check. Otherwise maybe I've done something wrong. So this is parallel to ABD, perpendicular, and this must be 30. Yeah. So you see I have 1, 2, 3, 4 solution, and then the other one will go somewhere here. Yes. Perpendicular. Yeah, and then I make sure that the angle is 50. So the 30 with ABD and 50 with ABC. Yeah, I need to double check because this is the typical thing that you always need to check if you don't want to make mistakes. So 50 with ABC and 30 with ABD. Yeah, okay, all good. As I've been using the same points, I keep the angle, so that's something good. But yeah, I could find the solution one by one if I want to. So this need to be parallel to ABC. This need to be perpendicular, and I think this angle will be 50. Yeah, I don't need to put it. Yeah, okay, so I have my four solutions. Yes. And then in the statement, they tell you once you have, taking into account the possible solution of R, calculate the minimum distance between R and C. And C is this point here, yes? So then, visually, I could picture which one will be the minimum distance. So for example, between here, this can be the minimum distance, or maybe this one of those ones. So I'm gonna check with this one and see. So from here to this segment, and has to be perpendicular. Yes. And this distance is 53.22, and maybe this one might be smaller. I will check. Perpendicular. Yeah, this one will be smaller. 35.02, and yeah, I don't think the other ones. Yeah, because this line go through there, so this one will go there, so I don't think it's gonna be smaller, and this one go there, so I don't think it will be smaller. So I think this is the solution, 35.02. I could double check all of them, but I don't think it's needed. And then we check at the solution is 35.02. Yeah. So I think that maybe the complex thing here is to find all the 4 possible solutions. If you're in an exam, maybe you can find only 2, and maybe you won't get the right one. Maybe you are lucky and you are one of those, but maybe you are not lucky and you get this and that, this solution and that one, which is not the right one. Yes. So I think it's good in that sense to be able to find all the 4 possible solutions. But yeah. Okay, so and we are going to solve now 9.2, which is the angle. Yeah, from all possible solutions, calculate the minimum angle between R and AC, which is this one. Okay, so then I draw a line here. And yeah, so for example, like, I could see here, maybe this one looks like a smaller angle with this one, or maybe that one, I don't know. But we are gonna check. So I will start with this one. For example, I say this is parallel to this solution. Yes, parallel. Maybe this, and then I'll find the angle. This angle is 51. Yes. This one, I don't think this is a solution because it will be like a very large angle. Maybe this one, so I will check with this one. So parallel to this one, and find the angle. Yeah, it's the same one because they are. So I think this should be the solution, is 51. Let's have a look. 9.2, yeah, it's 51. So although in this problem there are 4 solutions, 4 possible solutions, in the statement they already clearly said that from all the possible solutions you have to find the minimum distance, and here you have to find the minimum angle. So although, for example, this one and this one, they might be solutions, they will not the right one. They will fulfill the angles, but they won't be the solution. Yeah. So this is one method to find the solutions, and I'm going to show you another method. Okay, so this is as the traditional way, or the way that we have explained in class, where you do the perpendicular and parallel to the plane and get the angle. But I'm going to do a different one, which sorry, I said a two-dimensional sketch, but it has to be a 3D sketch. So we are going to use here the normals. Yes, solution using normals or perpendiculars. Yeah, and you have this here in the theory. Yeah, in the theory, when you have the construction, you have the direct construction, where you have the segment parallel and perpendicular, and there is an indirect construction where you find line R and the two lines normal to the planes alpha and beta in this case. And between the line and each of the normal lines, you need to find the complementary angle. Yes? And we can see that here already. So in this first solution, we measure the angle with the parallel, but we can make the complementary angle, which is 90 minus my angle, with the normal. So we are going to do this, and this solution is relatively helpful. I'm going to hide this one. Yes, and what we are going to do is we are going to do something like this. So I have one, for example, 1 point here, and they will be the normals. Yeah, I'm going to fix this point in the space, so I can move the lines, but not that point. The point is black because it's fixed. So then I make this line perpendicular to ABC. I make this line perpendicular to ABD. Yeah. So they are the normals to my angle. So now I make another line which will be my all possible solutions. Yes. And then what I do is I make an angle between this and the perpendicular to ABC, and here I said 90 minus the degree. My memory is not very good, so ABC, the angle was 50. Yes. So I have to put here 40. Yes. To get 90 minus 50 will be 40. So here will be 40. And here it will be 60, because 60 plus 30, which is 30, the angle between this line and this one and this plane have to be 30, so I put the complementary, which is 30. Not here, but there. 30. Here, I don't know why I cannot. I'm going to model it a bit. $60. Yeah, why? I don't know why it didn't work before. Okay. Yeah. So this is one solution, yes? But my solution, according to the statement, I have to start in this point D, yes? So, this is a solution, but I can find many different solutions. If for example, like if I move this normal to this, I will have another line that fill all these things. So what I'm going to do is I'm going to find all the possible solutions from point D. So from point D I have this one, and say that this one is parallel to this one. Yeah. Now I'm gonna fix it in the space. I will fix it. Yeah, that's fine. And then I remove the parallel. Yeah. So now this is fixed. So if I move this, I will get a different solution. So now we are gonna find another solution, which is this one. Yeah. So I make this parallel first, and one that is parallel, I fix it in the space. Fix and remove the parallel. Yes. So then I get another solution. So it should be parallel. I fix it and remove the parallel. And I think there is the last one that should be somewhere here. Take care that some solutions they are collinear with others, but I think will be maybe if I move this one here, this I got it already, this one I got it already, so this one is the one missing. Okay, so this is parallel and then fix and remove the parallel. Okay, so they are my 4 solutions, and they should be the same ones, but they are collinear. You see this one and this one, it is the same. Essentially, I'm gonna visualize it. I put it in the wrong direction, but that's fine, that's not an issue. Yes. So yeah, you see that they are my 4 solutions, and yeah, I can again compute my minimum distance and the angle. I'm not gonna do it because we see that they are the 4 possible solutions, so we have done that already. Okay, so this is another way to compute the angle between one line and 2 planes with the normals, but we need to be very careful with the angles because we have to put the complementary, yes, so 90 minus my angle, yes. Yes, okay, so this is the solution with the normals, and there is another method to solve it. To solve this, I'm going to hide everything. Sorry. There is another method which is a bit more, yeah, I think it's very visual, but maybe it takes a bit, it's a bit longer, but we can find that method here in the theory. So you see here it is plotting the angles with a cone, yes. So for example, when we have here a point and an angle, all the possible lines that form an angle with that plane, they will draw a cone, yes, like you see here. So using cones, we can do that thing. The problem of using cones is that if we want to move the cones within my SolidWorks domain, I need to add the cones as a new part. We done this already before in modeling, where we have an assembly and we add parts, but this is a part. So what I need to do is I need to convert this in an assembly. So if I go here to File, and there is here new open, make drawing from part, and here is a make assembly from part. If I click here, it is thinking, no, yeah, begin assembly. Okay, so I have an assembly here where within my assembly I have the statement with all the solution, but that's fine. And I'm gonna visualize my planes, yes. Okay, my planes. Okay, so what I'm going to do now is I'm gonna add cones, and I will, yeah, cones with a given angle, and I will with mates I will do it parallel. So for example, if I have a cone here, if I draw a cone where the base is parallel to this one, yeah, that's all the possible solution will be within that surface, yes. So for example, I go insert, component, new part, and I'm gonna already call it cone, I think it's 30 degrees with this plane, yes. 30 degree with ABD, 30 degree with ABD, yes. Okay, so I'm gonna make a cone of 30 degrees. And then you remember, if we want to modify this part within the assembly, I go to right click here, right click, edit, and then I ask for a two-dimensional sketch on the front plane, and what I only have to do a triangle, yes, which will be, I made it horizontal, and I don't want to do that because I want to be no fix. And then I make this and this one, yeah. So this line need to be perpendicular because this line will be the axis of my cone, yes, or the height. This is going to be the base, so I'm going to put the angle between those two lines, between the base and the generatrix. So if I put here 30 degrees, yeah, and I'm going to put a dimension already. For example, I'm going to put here 20 because I don't want to have a very big or very small cone. So you don't need to put the dimension, but it's just to have it. Yes. So now to build the cone, I go to features and ask for a revolution. So if the angle is between this one and that one, and this is the height, so the axis of revolution need to be this line. Yes. Okay, maybe it's a bit too big, but that's fine. Okay, so all this surface form an angle of 30 with the base, yes? So I will put my cone to float, yes, right click to float so I can move it. If I don't put it to float, I cannot move it. You see, I try to grab it, but I can't. So I put it to float, yes? And then, as my angle has to be with point D, so I click at the vertex, control, click at the annotation node, click at this point, and then go to mate and coincident, yes? And this base is parallel to that plane, parallel, yes? So all the solution, you see here the solution, if I visualize it a bit, you know, the solution, they are always on the surface of that cone, but not only on that one, but also the complementary. So for example, if I click on my cone, control and put it again, so I have two 30 degrees cone. So I go to here, this, well, I'm gonna rotate it a bit so you don't get confused. I'm gonna rotate this component and I will put it in the already in the size, in the right, more or less in the right. Yeah, and I find for the vertex this one, assembly, coincident, yes, and then I said that the base is parallel to my, okay, so you see my solution, they have to be always in the surface of that cone, yes, okay, but I need also the 50 degrees, yeah. So then what I'm going to do is I'm going to find a cone of 50 degrees. So insert component, new part. I will call it cone 50 and I edit it. I ask for a two-dimensional sketch again and do the same. So I said this line and this line are perpendicular and I put the angle between this one. The only thing here important when we make cones is that the angle have to be between the base and the height. You know, if this is my cone, this is the base and the height, so the base and the height have to be perpendicular and the angle is always here. Yeah, don't do, for example, the angle here, because then we need to be careful how we do the revolution. That's the only thing. So we put here again 20, so they are similar size, and make the revolution with this axis. Take care, don't do it with this one, because the angle won't be 50, will be 90 minus 50. Okay, so then I have my cone. I cannot move it because by default SolidWorks make it fixed, so I put it to float. And what I do is I make it coincident with that point, the vertex, yes. And I will make the base parallel to plane ABC. It can be on that direction or the other one, doesn't really matter. Parallel, yes. So my solutions, I have 4 solutions, will be the intersection between this one and that one, and this one and that one. And we can already see that because we already compute the solutions. Well, yeah. These 2 solutions and the complement and the collinear to this one. So in order to find the solutions, I can go to a 3D sketch here within the assembly, a 3D sketch, and I can do 2 things. One is, for example, I can do the convert entity or intersection curve. This will plot the intersection between 2 solids. So if I go to intersection and I click this one and that one, accept, you see, make the intersection, and between this one and this one, and make the intersection. Yeah, that's one way to do it. Another way to do it is make a line between the vertex and anything. Well, I can say that this line is with this surface, so I click the line and the surface and say, yeah, maybe tangent, but I think if we make this segment being on the base, then it will be already on this cone, you see. And then if I said that this point have to be also coincident with this one, yeah, it will give me this solution, yeah. Anyway, I found the 4 potential solutions, but we can have this one, for example, or the collinear one, which can be this one. They are exactly the same solution. Collinear, no. Collinear, yes, but in the right, in the other direction, yeah. And then you see that they are the same solutions that we plot here. You see the blue ones are this one and that one is this one is the collinear, and this, yeah, they are the collinear ones. So they will be my 4 solutions. This one, the collinear to this one, the collinear to that, and that one, yeah. So you see 3 different methods to solve this one, and yeah, as we have 4 solutions, we will need to just go to a statement and find which one of those 4 solutions have the minimum angle, or which one has the minimum distance. I hope it is clear enough, but it is not, please let me know, drop me a line or send me an email, and then we can discuss it. Good luck trying to find it.